I'm sorry that I didn't know YouTube actually doesn't allow me to upload video clips that are too long. So this is actually part 4 of our section 5.4, which discusses example 3 to solve this recurrence relation. And we apply the same idea as in example 2 by setting up the general form of generating function for an. Okay, we call that f of x. And because of the 5 in front of a n minus 1 and 6 in front of a n minus 2, we're going to calculate 5x times f of x and 6x squared times f of x individually. Again, make sure that you line them up in a way that x terms with the same power show up in the same column. Okay, and then if we take one copy of the first row minus the second row plus the third row, look at here what we will get in general for the right hand side. We will see an minus 5an minus 1 plus 6an minus 2. Of course, if you pull out the xn terms. Okay, so the coefficient will be exactly the left hand side of what we have in this standard form of the recurrence relation, which makes it a 0. Okay, so that is what will happen next. But if we do that process for everything one by one, the left hand side will look like that. 1 minus 5x plus 6x squared, f of x is put out. And we have a0 survived. And for x terms, the coefficients can be combined as a1. Remember, that's a minus in front of 5a0. Okay, a1 minus 5a0. And for all the remaining terms, you could go ahead to pull out the common x power, and then the coefficients, according to the recurrence relation, are all zeros. Therefore, all those from here are gone. The next step, we will just take advantage of our knowledge of a0 and a1 and plug those numbers into these terms here, and we have this equation. Okay, divide that parenthesis over, we have f of x equals to this. It's a rational function with a linear term for the numerator, and it's a quadratic in the denominator. And we can rewrite that into a form of partial fractions. The reason we want to do that here is because we cannot apply that identity we want to use to expand this rational function immediately. But we can definitely apply the identity we know very well of to these two, each of them individually. Okay, so we're going to factor out the denominator into this form. It's a product of 1 minus 2x times 1 minus 3x, and we know that the general form for the partial fraction would be like this sum. If you don't recall, if you don't remember much of the details of rewriting rational functions into sum of partial fractions, please revisit your calculus material, and by all means, you're welcome to come to me and ask questions for the detail of this step. After we evaluate those undetermined numbers a and b, we will find out that a equals to -1 and b equals to 3, which makes this rational function equals to -1 over 1 minus 2 plus 2, which is the value of b, divided by 1 minus 3x. Okay. Now if we rewrite each of them into these forms, we know how to rewrite each of these fractions into the form of the expanded version. Indeed, we will have -1 times the bracket of the expanded version plus 2 times the bracket of the expanded version. which is that. Okay? If you don't know how to get here from there, you probably want to review the second video clip in this section. Once we have this result here, we can go ahead to simplify the expression in a way that distributing all these into the brackets, distribute -1 here, distribute 2 here for each of these, and then we're going to combine x terms with the same power. So the constant term will be -1 times 1 plus 2 times 1, and the x term will have the coefficient as -1 times 2 plus 2 times 3, and so on. Okay. In general, we will have -1 times 2 to the n plus 2 times 3 to the n, like here. I hope this is suggesting, I hope this is clear that it's suggesting a complete description for an would be like that. Okay, so our answer to this question for this question is an equals to -2 to the n plus 2 times 3 to the n for each n that. So for all n that is greater than or equal to 0. You're welcome to try to plug in several n's to see whether this formula works for an. Okay, and also recall the characteristic equation method. You're welcome to apply that to the same recurrence relation and compare that your answer with this method. You should be able to find them equivalent to each other.